Welcome to the tutorial series on network analysis made simple. During the previous tutorials, we have studied different methods of network solving such as branch current method, node voltage method, super mesh concept, super node concept, and also we have studied the Thevenin's theorem. During this tutorial, we shall study the network solving using Norton's theorem. Friends, Edward Laurie Norton was born on July 29, 1898 in Rockland. Initially, he started his career as a radio operator in US Navy for 2 years. Then he graduated in 1922 and joined Western Electric Company, the predecessor to Bell Telephone Laboratories. There he earned his master's degree in 1925. You see, he remained with Bell Labs all of his career and retired in 1963. During his 41 years of service, he wrote only 3 technical papers, but he wrote 92 technical reports. In one of his reports titled Design of Finite Networks for Uniform Frequency Characteristics in 1926, a short paragraph describing the current source equivalent appeared, and it was the relation of ratio of input and output currents in a network, and that we call it as a Norton's equivalent circuit. Friends, before we go into the study of Norton's theorem, we shall recall Thevenin's theorem. We know that the Thevenin's theorem transforms the given network into a single voltage source network across the load branch as shown in figure 1, and the load current IL is calculated using IL equal to V Thevenin divided by R Thevenin plus RL. Whereas Norton's theorem transforms the given network into a single current source network across the load branch as shown in figure 2, and the load current IL is equal to Rn divided by Rn plus RL into IN, where IN is called as Norton's current and Rn is called as Norton's impedance. Now we should know how to find out IN and Rn. For that, consider a network shown in figure, and if we solve this network using both the theorems, the result has to be same. What does it mean? The Thevenin's equivalent circuit should be same as Norton's equivalent circuit. Now, for the two circuits to be equivalent, what is the terminal behavior? The terminal behavior is the voltage appearing across the terminals A and B of both the networks. Now, if you consider Thevenin's equivalent circuit shown in figure 2, VOC is equal to V Thevenin because current through R Thevenin is 0 as A and B are open. Similarly, now what shall we do is, we shall short circuit the terminals A and B and find the short circuit current ISC, and we see that ISC is equal to V Thevenin divided by R Thevenin. Now, for making the Norton's equivalent circuit to be equivalent to Thevenin's equivalent circuit, what shall we do is, we shall make IN is equal to ISC and Rn is equal to R Thevenin. If so, in the circuit shown in figure 4, you see that IN will flow through Rn and the voltage between A and B is IN into Rn, and that also is equal to ISC into R Thevenin, but ISC is equal to V Thevenin divided by R Thevenin, and hence we get voltage across AB is equal to V Thevenin. It means in both the Thevenin's and Norton's equivalent circuit, the terminal voltage VAB is V Thevenin, and hence both the equivalent circuits are equivalent to each other. Now you may be thinking, is it not the converting voltage source into current source? Yes, definitely friends. It is here we are converting the Thevenin's equivalent circuit, which is a voltage source, into a equivalent current source. That's all. Friends, Let me quickly summarize the procedure of solving the network using Norton's theorem. Step 1. As usual, visualize the given network, identify the junction nodes, branches, independent loops, and the types of sources. Step 2. If the load branch is not separated from the rest of the network, modify it. Step 3. To find VOC, open the load branch, keep all the sources and the circuit to the left of the terminals AB as it is and find VOC. Step 4. To find ISC, short circuit the terminals A and B, keep the rest of the circuit as it is and find ISC. Step 5. Calculate Rn using Rn is equal to VOC upon ISC. Note that this procedure necessarily should be followed for the networks containing both dependent and independent sources. Step 6. Draw the Norton's equivalent circuit as shown in figure 5 and find the load current IL using IL equal to Rn divided by Rn plus RL into IN, and note that IN is equal to ISC. Let us take up an example to determine current Ix in the load resistance of 5.5 ohm in the circuit shown in figure 1 using Norton's theorem. You see that the given network has two junction nodes, two independent loops and three branches. It has two independent voltage sources, one of 3 volts and the other of 4 volts. It also has one independent ideal current source of 2 amperes. It has one current controlled voltage source of 0.5 Ix volts. Therefore, because the network has the dependent voltage source, to find Rn, we have to find both VOC and ISC. Hence, to find VOC, we have to open the load branch as shown in figure 2. Opening the load branch has resulted in Ix equal to 0. In turn, the voltage of the dependent voltage source 0.5 Ix also has become 0. We know that a zero voltage and a finite current implies short circuit, and hence the dependent voltage source is to be short circuited. And if you do not understand this, I suggest you go through my earlier tutorial video on open circuit and short circuit concepts. Friends, the circuit is redrawn by short circuiting the dependent voltage source as shown in figure 3. You also note that opening the load branch has resulted in a single closed loop network. Hence, the source current of 2 ampere will circulate in the loop as shown. Let VAB is equal to VOC, the open circuit voltage. By writing the Kirchhoff's voltage equation for the outer loop, tracing it in the clockwise direction, we get VAB minus 4 into 2 plus 3 is equal to 0. By solving it, we get VAB is equal to 9 volts and hence VOC is equal to 9 volts. To find the short circuit current, the terminals A and B are shorted as shown in figure 4. Now, Ix is the current flowing through the short circuited branch, therefore Ix is equal to ISC. To find Ix or ISC, let us choose a branch current method. By applying Kirchhoff's current law to junction node 1, we see that the current flowing through 4 ohm resistance is 2 plus Ix amperes as shown. Now, there is only one unknown, hence only one loop equation is to be written to find the unknown. Friends, to find ISC, Rn and the load current IL, the circuit obtained earlier is reproduced here. And we also know that VOC is equal to 9 volts. And in the network, there is only one unknown, and hence by writing the Kirchhoff's voltage equation for the outer loop, tracing it in the clockwise direction, we get minus 4 into 2 plus ix plus 3 plus 0.5 ix equal to 0. By solving it, we get ix equal to minus 9 divided by 3.5. Since the answer is negative, what does it mean? The assumed current is flowing from A to B, but the true current is flowing from B to A. But we know Ix is equal to Isc, and hence Isc is equal to 9 divided by 3.5 amperes. Now we know both VOC and Isc, and hence we can calculate Rn using Rn equal to VOC upon Isc. By substituting the values, we get Rn is equal to 3.5 ohm. Now, knowing In and Rn, the Norton's equivalent circuit drawn is shown in figure 5, and IL is equal to Rn divided by Rn plus RL into In, and by substituting the values, we get IL is equal to 1 ampere. Friends, let us take another very interesting problem. The network is enclosed in a black box as shown in figure 1. When RL is equal to 10 ohm, current through it is found to be 2 amperes. When RL is equal to 20 ohm, current through it is found to be 1.5 ampere. Find the load resistance RL when the current through it is 0.6 amperes. Now, if you observe the given network of figure 1, the network in the black box can be assumed to be either a Thevenin's equivalent circuit or a Norton's equivalent circuit. Let's assume it to be Thevenin's equivalent circuit. Let the Thevenin's voltage be V Thevenin and the Thevenin's resistance be R Thevenin. We also know that the equation for the load current IL is equal to V Thevenin divided by R Thevenin plus RL. Now, for obtaining the unknown values of V Thevenin and R Thevenin, two sets of values of RL and IL are given in the problem statement. Using these values, two equations can be obtained. Equation 1, when RL is equal to 10 ohm, the current through it is found to be 2 ampere, from which we get 2 is equal to V Thevenin divided by R Thevenin plus 10, and by rewriting it, we get V Thevenin minus 2 R Thevenin is equal to 20. Let it be equation 1. Friends, the equation 1 V Thevenin minus 2R Thevenin is equal to 20 is reproduced here for convenience. To get equation 2, when RL is equal to 20 ohm, current through it is found to be 1.5 ampere, that is given, and hence we get 1.5 is equal to V Thevenin divided by R Thevenin plus 20, and by rearranging it we get V Thevenin minus 1.5 R Thevenin is equal to 30. Let it be equation 2. By solving the two simultaneous equations 1 and 2, we get V Thevenin is equal to 60 volts and R Thevenin is equal to 20 ohm. But we are required to find the resistance RL when the load current through it is 0.6 amperes. So, knowing V Thevenin and R Thevenin and using the equation for IL, we can find RL. By substituting the values, we get 0.6 is equal to 60 divided by 20 plus RL, and by solving it, we get RL is equal to 80 ohm. Friends, don't you feel that this is interesting? Friends, to emphasize the concept that we have learnt, let's take another very interesting problem. To find the current IL in the load resistance RL is equal to 3 ohm in the network shown in figure 1 using Norton's theorem. First, let us visualize the network. It has 4 junction nodes, 3 independent loops and 6 branches. Also, it has 2 independent voltage sources, one ideal voltage source of 5 volts and the other of 5 volts in series with 10 ohm. It also has one ideal current source of 2 amperes. To find the Norton's current IN or ISC, open the load branch as shown in figure 2 and short the open circuited terminals A and B. Now, if you observe the network, it has one ideal voltage source of 5 volts and one ideal current source of 2 amperes. Therefore, we can solve the network for IN using either supermesh concept or using supernode concept. Friends, we can also solve it by using branch current method. Now, I will decide to solve it by branch current method and you can try to solve by other methods and see that you get the same answer. Friends, to find IN using branch current method, the circuit is redrawn as shown in figure 3. Let IN be the short circuit current in the branch flowing from 4 to 1 as shown in figure. Using Kirchhoff's current law, we have to find all the branch current equations. Hence, applying Kirchhoff's current law to junction node 1, current in the branch 1 to 2 will be IN plus 2 amperes. Let I1 be the current in branch 2 to 3 as shown in figure. By applying Kirchhoff's current law to junction node 3, current in branch 3 to 4 will be I1 minus 2 amperes. Similarly, by applying Kirchhoff's current law to junction node 4, current in the branch 4 to 2 through 5 volt source will be I1 minus 2 minus IN amperes. Now let us check whether our equations are correct or not. At junction 2, if we find I1 minus 2 minus IN plus IN plus 2 is equal to I1, which is the current flowing through 2 to 3, it means our all branch current equations are correct. Now, you will be surprised to see that if we write only one loop equation, we can get the value of IN, and that is the beauty of it. Hence, by writing the Kirchhoff's voltage equation, tracing the loop from 2 to 1 to 4 to 2, we get 2 into IN plus 2 minus 5 is equal to 0, from which we get IN is equal to 0.5 amperes. Friends, the solution is so simple, isn't it? Friends, to find Rn, let us use procedure 1 because the network contains all independent sources. Now, what is procedure 1? Open the load branch, make all sources 0. To make the voltage source 0, short circuit it. To make the current source 0, open circuit it. And look into the open circuited terminals and reduce the network and get Rn. That is what is procedure 1. Hence, by making all sources 0, the circuit drawn is shown in figure 4. Now friends, keenly observe the network. You find that 10 ohm and 2 ohm resistances are short circuited. Hence, by shorting these resistances, the circuit drawn is shown in figure 5, and if you observe, you will be surprised to see that straight away we get the Norton's resistance Rn equal to 2 ohm. Friends, now are you convinced that identifying the connectivity of the network elements in a network is so important? Friends, we know IN is equal to 0.5 amperes and Rn is equal to 2 ohm. So knowing IN and Rn, the Norton's equivalent circuit across the load branch drawn is shown in figure 6. Hence, we can find out IL using IL equal to Rn divided by Rn plus RL into IN, and by substituting the values, we get IL is equal to 0.2 amperes. Friends, I hope that you have started smiling and thinking without your knowledge, because the solution of this problem is so interesting. Friends, network solving is an art. It demands desire, dedication, and continuous practice. I suggest you make it a habit of solving each problem by different methods. Whatever the method that you follow, the results are to be same. Friends, number of issues required to be known to solve networks using Norton's theorem are brought out by solving typical examples in this tutorial. I hope this tutorial has ignited your thoughts. If so, please forward your suggestions and feedback to my email. Thank you for watching this video.